Welcome to class today. When we last met in person, we were talking about cameras and how the eye can see. Today, we're going to talk about cameras, pixels, lenses, and in particular, pinhole cameras. So remember when we last met and we were talking about how where you have the eye can see various wavelengths, where we have starting out with our blue sensor in our eye, the green one, and red. So what we have here are the various ways that how it integrates over each of these wavelengths to get a reading. Well, a camera does a very similar thing, except so the camera is also going to have these types of sensors that respond to various wavelengths. And you may know that a camera is actually divided into pixels, and each of them has a different sensitivity to various wavelengths. And if you think about how you can lay out these RGB pixels, so we have our red, green, and blue. So when we have this grid, we need to figure out how to lay out these pixels, our RGB pixels. And the most common pattern here we have is called the bear pattern. And in the bear pattern, what we do is we actually alternate in one row B, G, B, G, B. And so this has, one row just has blue and green, and the other one has green and red. And then we go back to alternating blue, green, green, and below this we now repeat where we have green, red, and so on and so forth. So this is what the pixels on a camera look like. And one of the key factors is that the bear pattern has twice as many green as red. It turns out that this is actually a good thing, because human eyes are actually twice as sensitive or more sensitive in green anyway. So having more green sensors actually makes sense. Now, the next question is, when we have these pixels, how do we actually get them off the camera? So how do we get data off of the camera? And I'm not talking about at the very highest level, I'm talking about each pixel. Well, it turns out that it's very expensive to try to actually read to have the data collected from each pixel. So what happens is that we typically do this basically row by row, where you actually are collecting first the top row and then each successive row. And that's because in this, what happens is basically we have a special unit on the side here where these are able to actually read the value. And what happens is that each of these pixels, the data is basically shifted one by one over and over, so that we get all of the data off and read by each row. Now, this actually makes the sensors on these cameras much cheaper, because we don't have to have the expensive electronics here reading all of the pixels. We can just have one row doing this. So this saves a lot of money on this, but it also poses another problem, because what this means is that we can't read all of the pixels at once. So this can cause problems where we can actually get motion blur. so we can get some type of, get some of motion blur caused by this. And check out the YouTube video I linked to in Canvas to see how this happens. And this is called a rolling shutter. And the rolling shutter basically has this problem. So if we want to avoid this problem, we need to do something with a global shutter. So a global shutter system, basically what this does is it reads all pixels at the same time, or in contrast, or what they do is they basically freeze each pixel and then read them off sequentially. So why does this matter? That's the thing why do we actually care about this? And the reason is that robots are often moving around, and we care mostly about what happens when you're moving quickly, and objects may actually not be, as they appear. So, okay. So when you're working with robots, with cameras, it's very important to know if you have the rolling shutter or a global shutter to know if you're going to get some of these blur effects that rolling shutters cause. And again, check out the video that I've posted on Canvas on this. Okay, so we've talked a little bit about how the data is actually stored and read off of a camera. Now I want to talk about kind of the basic camera model, which is known as a pinhole camera model. So the pinhole camera model is the basic camera model that is commonly used, and what it is that the idea is that we have some sort of pinhole here, and we have some object that we're trying to take a picture of, and basically what happens is that this pinhole map is basically how we map this onto the sensor. So this is our sensor. And if we are then basically the rays of light come through this pinhole, and we might have some other one where that's not very good. Basically, so what we see is that from this person out here is going to be mapped to some other person on the sensor, and one of the things is that this person mapped on this sensor is actually going to look upside down. But with this, we can actually start to understand a little bit more about how cameras work and how we can actually figure out the geometry of objects in the real world based on what we're seeing in the camera. And this is important because in robotics, we care about how big things are in the field, and we don't just want to know analyze if there's a dog or cat in that picture. We actually want to be able to see where the cat is and figure out how to track it. So we can expand on this now a little bit and draw this pinhole diagram again. And instead of actually drawing the hole, instead I'm going to label this axis. Let's call this X1, and we will draw another axis here. So this is going to be in the world, and this is our camera. And we are going to have our image plane here. So this is our image plane. And what we can do then is if we have some object in the world, let's say it's right here. So let's say this is an object at point P. Well, we can now start measuring things in the world. So we can say, let's say this is called XY, and if we look and figure out how this intersects our pinhole plane, what you can see is that you have two similar triangles here. So these similar triangles, if you recall from your geometry class, this lets us actually compute some additional geometry here that we can use to figure out how big things are in the world, how big they'll show up on the plane here. So if we label a few more things here, let's call this one z. So this is the distance to the object in the world, and what we call this in the camera is f. So this is the focal distance, and we're going to call this measurement little y, which will be basically this is how many pixels in the camera frame. And with this we can then actually calculate how far away something is or how big something is in the real world. So what we can say is that if we have, do some similar triangles here where we have y over f is going to equal, and we're just going to call this x, y over z. So now if we want to know, how many pixels it'll take to, an object in the real world at some distance, we can say, y is going to equal f x y of z. Or similarly, if we know how big something is in the world, and we know how our focal distance, and we know how many pixels it is on the camera, we can then solve for the distance to the object. So this lets us say, if we flip this around, right, we can say now basically z is going to be equal to the focal distance over the ratio of the object in the real world and the number of pixels. So this lets us actually get the distance to an object in the real world if we know our focal distance and the height of that object in the world. So this is useful because we can then actually use things like, if we know the size of a box in the real world, we can then use the measurements from our camera to figure out how far away it is and where it is by seeing where it is in the image plane. So you can obviously extend this beyond just the 1D example here to 2D, and it's all just a lot more geometry. So what I want to talk about now is some other properties of cameras. So the reality is that this pinhole model works well to think about the basic geometry, but that's not how a real camera works. So instead, cameras actually have lenses, and the quality of the lens matters. They have something called the dynamic range, where basically how well it can reproduce very bright or dim objects. So some of these properties that we care about of cameras include things like the lens quality, the dynamic range. So this is, again, dynamic range is the ability to reproduce very bright or dim objects. There's also, things related to this are things like the aperture. So the aperture is basically, how much light is being let in. There's also things like the film speed. Even though we don't have film anymore, there's still this thing called the speed, which is basically also known as the ISO of the camera. And then we need to know things like the focal length and the field of view and a number of other factors. But with these, we can actually then compute a lot more about the images in the camera. And when we have these, what we need to do then is actually figure out how to correct for these kind of potential errors in the camera itself. And this is known, especially with the lens, where you might have things like barrel distortion or other types of distortions. You can see that it is possible to fix these if you are able to calibrate the intrinsic parameters. So The intrinsic parameters basically are the things that characterize the optical and geometry of the camera itself. So that this perspective model, which is what the Pinhole camera is known as, is actually correct. So this basically is a way to calibrate the optical, geometric, and other internal camera parameters to get to a perspective model. And the perspective model is basically this Pinhole model that we talked about. Now that we've talked a little bit about Pinhole models, while you're at home unsure what to do, you can actually experiment with a Pinhole camera. So we all know how valuable this stuff is these days. So if you have some of this, you know you don't want to waste it. But when you're done with that, you get these. And with a little science project, you can actually create your very own Pinhole camera. So what you can do is take a couple of rolls, and at the end of one, put a very dark surface with a very small hole in the middle. And then in between, use some sort of translucent paper and put it in the middle of here and tape it together. And you've got basically a little telescope type thing that if you shine it look at pretty bright lights, you can see actually the projection of the image that you're seeing through this little hole on the sheet, which is your image plane. So again, if we're to map this to our the diagram we drew, basically, our image plane is in the middle, and this distance from the pinhole to that image plane is the focal distance. And so you can actually get things to project here and make your own little camera. So a good science project to do while you're stuck home.